UT Austin. Used to be a professor at MIT, so maybe some of you know him from this area. And he's going to tell us about gentle measurement of quantum states, differential privacy. Thank you.
All right, well, thank you so much, Ryan, for arranging this. It's a privilege to be here. So, so I want to tell you about some joint work with Guy Rothblum from the Weizmann Institute that we did last year. It looks like someone is locked out. Oh, no. Okay. And, this was really represented sort of an unusual sort of coming together of two very different areas. Differential privacy, that's about protecting people's data, and Facebook or medical records or things like that, and measuring quantum states without disturbing them too much. Those sound like pretty unrelated problems. So the point of this talk will be to prove to you that they're not unrelated. And I apologize that this talk is probably a little bit outside of the wheelhouse of the usual topics of CMSA. It does have theorems in it. It is I guess math, inspired by questions in physics. You could say in this case, quantum information or foundations of quantum mechanics. This, we have a paper on it, and it appeared in the stock conference this past year. Okay, so I have one slide to just explain the basics of quantum mechanics insofar as I will use them in this talk, or just to make sure that we're all on the same page with the terminology and notation that I'll be using for quantum states and measurements of quantum states. Okay, so a mixed state, or a density matrix, is the most general kind of state that's allowed in quantum mechanics. It's can be represented or can be thought of as a probability distribution over different quantum superposition states, where let's say the superposition psi sub I, which is some unit vector, and for us it'll always be a finite dimensional complex Hilbert space. And psi sub I occurs with probability p sub I. We have that ensemble, then we form a matrix rho by sum over all I of p sub I times the outer product of psi sub I with itself. That gives us, if it's a d-dimensional collection of d-dimensional quantum states, this gives us a d by d matrix, which happens to be Hermitian and positive semi-definite, and it always has trace of 1. Okay, and every such matrix is a quantum mechanical density matrix. And the interesting part is that one and the same density matrix will, in general, have infinitely many different decompositions of this kind. Okay, so it is not uniquely represented as a probability distribution over pure states or superpositions, but can be represented like that in infinitely many different ways. Okay, now we'll be interested in this talk in measurements of quantum states, and the most general kind of measurement that's sort of allowed by quantum mechanics, the kind that we will deal with in this talk is what's called a positive operator valued measure, or a POVM. Okay, and this encompasses, if you just know the sort of projective measurements, where I would just pick an orthogonal basis of unit vectors, and then my state, let's say, rho would collapse to the vector v when I measure, with a probability that is equal to v rho v, right? Which is just the mixed state version of the famous Born rule of quantum mechanics that probabilities are given by the squared absolute values of amplitudes. And a POVM encompasses that type of measurement as a special case, but it also encompasses even measurements that would act on both the quantum state rho that I am trying to measure, as well as some ancillary system, right? And so I could make a measurement on a d-dimensional system that has more than d possible outcomes, for example. Okay, and but even situations like that are still captured by the POVM formalism, and the way that it works is that let's say that I want to make a measurement with k possible outcomes. It will always be a finite list of outcomes in this talk. I am a computer scientist. Okay, but for each outcome we associate a matrix. So E1 up to EK. These matrices will always sum to the identity. And then the rule is that when I apply this measurement, it will return the outcome I with probability trace E of EI times rho. Okay? And you have to do a couple lines of algebra to say it, but this is really just a restatement of the Born rule in a different language. Okay, or in a more general framework. It's not introducing a new law of physics. And now in specifying a POVM, there's a very, very important part that I've left unspecified, which is, well, what is the state, assuming that what is the new state, assuming that the measurement outcome is I, right? So this formalism does not tell me what are the post-measurement states. And in fact, for one and the same POVM, there could be infinitely many different ways of implementing that POVM, okay? Whereby in implementation, I will mean the POVM together with sort of a specification of what are the post-measurement states, okay? And basically the way that works is that I can, each of these EIs could have many possible square roots, matrix square roots, right? Called AI, and for every possible way of taking square roots of these matrices, I could let the post-measurement state, let's say if AI is a square root of EI and the measurement outcome is I could have the measurement outcome, have the post-measurement state assuming the outcome is I, be that. Okay? So basically just the normalized version of AI row, AI dagger. Okay? Yeah.
Sorry, can you say a few words about why the measurement had to summing up to the identity?
Oh yeah, because so that is just the reflection here of the fact that the probabilities of all the different outcomes should add up to 1.
No, but these EI themselves are matrix, right?
The EIs are matrices,
EIs are
right?
not
But now
matrices,
what
right?
we want is the
Not
property, we want the property that these guys will sum to 1, okay, for every row, right? And that will hold as long as the EIs sum to the identity.
So these are not independent measurement.
Well, these are all the
states.
different possible
I
outcomes
see.
of
I
one
see.
measurement,
Got it.
okay?
Got it.
So we're applying one measurement, each EI represents a possible outcome of the measurement, okay? And then, the condition that they sum to the identity just gives us conservation of probabilities over here. Yeah. Okay, and then the one last thing that we will need is a distance metric on the set of quantum mixed states. Okay, and the most useful metric, at least for quantum information, is something called trace distance. Okay, and you can define the trace distance between two of these density matrices, so call them rho and sigma, as just 1/2 the sum of the absolute values of the eigenvalues of rho minus sigma. Okay, so it's just sort of the trace norm of rho minus sigma. Okay, so this is a distance metric. You can check that, and better yet, it has a clear operational meaning. Okay, the trace distance between two mixed states represents the largest possible bias with which those two mixed states can be distinguished by a single measurement, right? Like if I want a measurement that that can either accept or reject, and I want to maximize the difference between the probability that this measurement will accept rho and the probability that that measurement will accept sigma, right? Then trace distance tells me precisely what is that maximum distinguishing bias. Okay. So it's a generalization of total variation distance between probability distributions. In fact, it reduces exactly to variation distance in the special case where rho and sigma are diagonal matrices, right? Which basically just means they are classical probability distributions over d different outcomes. Okay. So now, I told you about measurements of quantum states. So what do we mean by gentle measurement? Famously, a measurement in quantum mechanics is an inherently destructive operation, right? If I take, Schrodinger's cat, before I opened the box, it was in, could have been in some arbitrary linear combination of alive and dead states. Okay, I open the box, I force it to make up its mind, whether it be alive or dead, with probabilities given by the squared absolute values of the amplitudes, and once it makes the choice, it sticks with it. Okay, and then all the additional information that was there about, let's say, the relative phase between the two amplitudes and so forth, that's all lost. Okay, some people would say it is literally in another parallel universe. Okay, or it is, but in any case, it is no longer accessible in our universe. Okay, but having said that, not all measurements on all quantum states are destructive. So, for example, if I knew that a qubit was either in the 0 state or the 1 state, well, then I can measure to ask which it is, and that will not damage the qubit at all. Okay, that's as possible because 0 and 1 are an orthogonal basis for the two-dimensional space of one quantum bit or one qubit. Okay, and this non-destructive measurement of classical information, this is why books are possible, for example. Okay, admittedly, when my 2-year-old son, reads a book, that is a destructive measurement. Okay, and the pages do get ripped. Okay, but the point is, in principle, that measurement could have been implemented in a way that was non-destructive. Okay, so now but now we'll be interested in this talk in measurements that might damage quantum state, but only by a little bit. Okay, and these are what we term gentle measurements. So we need a more formal definition. So given some quantum POVM measurement, say m, we're going to call m alpha gentle when it acts on some subset of states S. Which might be all of the states, but might be some strict subset of them. We'll call it alpha gentle on S if for every state rho in that set and for every possible outcome Y of measuring rho, this inequality holds. So the trace distance between rho and the post-measurement state, assuming that the outcome of the measurement is Y, is at most alpha. Okay, or in other words, applying the measurement and then conditioning on the measurement outcome being Y, that should damage the state, leave me with a new state that differs from my old state by at most alpha in trace distance. Yeah?
With this definition, then, like classical measurements of diagonal states are not gentle.
Yeah, that's right. That's right. Well, so sorry. I mean, you could say they are gentle when applied to the eigenstates or to the sort of definite states. But in general, I could measure a state that is in a classical mixture, a classical probability distribution, and that might not be gentle. Yeah, that's absolutely right. More generally, gentleness will be too stringent of a condition to possibly achieve for all states, as in fact your example, of classical distributions already shows. Okay, but we will try to achieve gentleness for interesting subsets of states. Okay, I will come back to that. Okay, right. And specifically, you know, a typical choice for the set of states S on which we will try to be gentle are the product states. That is, you know, states, let's say on n different registers, you know, or n different subsystems that can be written as tensor products, right? Meaning that they have no entanglement between the registers, and in fact, not even any classical correlation between the registers. Okay, but you know, just states, sort of n separate states. Okay, and we will see how even when gentleness sort of cannot be achieved on all states, it can very, very often be achieved on this sort of very relevant subset of states. Yeah.
Where coefficient 1/2 comes from?
Oh yes, the 1/2. That's just inherited from like the classical variation distance between distributions, because we would like the maximum distance between two distributions to be 1, right? But without the factor of a half, the maximum distance would have been 2. That's all. Right. So you know we just want, you know, 0 to mean that the distributions are the same, and 1 to mean that they are maximally, you know, they are distinguishable with a bias of 1, or perfectly distinguishable. Okay, good. So let's see an example. Okay, so let's say that I have n unentangled qubits. Okay, so I just have a collection of qubits. They might all be in different states. So, you know, like these alphas and betas might be different for each qubit, but for simplicity, we could even just imagine that they're all in the same state. Okay, meaning that I'll now have alpha 0 plus beta 1 tensor n, right? So I just have n qubits that are all, you know, in this superposition state. Okay, now let's say that the thing I want to know is the total number of ones. Okay, this would be a very common situation in physics. Like, you know, I have a whole bunch of modes that could be in a superposition of having a particle, you know, 1, and not having a particle, 0. And now I want to know the total number of particles that I've got. Okay, well, unfortunately, if I just implement this naively, this could be a very destructive measurement. Okay, why? Well, because this state, if I expand it out, is just a superposition over, you know, all possible strings of n bits, right? And if I look at the sort of the number of ones in the string, you know, for in computer science needlessly fancy terminology, the Hamming weight. If I look at the Hamming weights of the strings, well, these are just, these will follow a normal distribution. You know, if it were equal superpositions of 0s and 1s, then the mean, of course, will be n over 2. The standard deviation will be of order square root of n. So, you know, I will have what physicists might call a Gaussian wave packet, you know, a superposition over Hamming weights that is centered at n over 2 and that sort of falls off in a Gaussian way around that. Okay, but now the problem is if I measure the Hamming weight, then I localize this wave packet to a single Hamming weight, right? Like, let's say this one, right? And that, of course, you know, destroys the state. That's a very destructive thing to do. Okay, so is there a different way that I could measure where I will learn the Hamming weight to a very high precision, but without damaging the state? Okay, well, it turns out that there is such a way. And, you know, in fact, you know, experimental physicists have known such things, you know, for a very long time. But the key idea is that I can, before I make the measurement, I can deliberately add some noise to the Hamming weight. Okay, so I can sort of deliberately noise my result, sort of obscure it a little bit. So let's say that I make a measurement that will only tell me the number of ones plus some, for convenience, let's say Laplace noise, you know, of some mean value that is large compared to square root of n. Okay, so Laplace noise is just noise that follows this distribution. Okay, it's like Gaussian noise, except that instead of the square up here, I simply take the absolute value. Okay, so it falls off, you know, exponentially, but a little bit more slowly than Gaussian. And so I could add Laplace noise, and what I can do is, by designing a suitable quantum circuit, I could make a measurement that will only tell me, not the Hamming weight of x, but only the Hamming weight of x plus the Laplace noise. Okay, so using unitary transformations, or using valid quantum mechanical operations. One way that I could do this is to just prepare a superposition over all of the possible values of this Laplace noise, and then do a unitary transformation that just takes the Hamming weight of x and adds it, coherently adds it into the second register. Okay, I can build a little circuit that does the addition. It will generate some garbage along the way with which it will be entangled. There's a standard trick in quantum computing to get rid of the garbage, which is called uncomputing. Just running my whole circuit in reverse while leaving only the answer. Okay, so I can do this and then make a measurement only of this second register. Okay, and intuitively what that does is that for each possible Hamming weight, well, it gives me some distribution over possible outputs that I'll see that is Laplace distributed, right? But now the key point is that for two nearby Hamming weights, these two distributions will mostly overlap, right? So I will not be able to learn from the measurement outcome alone whether I was exactly here or whether I was a little bit over to the side, right? And because I haven't learned that, you can do a calculation that will tell you that, your post-measurement state will actually be very close to your original wave packet. Okay,
Can I
yeah.
ask a question? Because
Sure.
I can see where you go from here to the differential privacy because
Oh, really? Okay.
you're very
You're
close.
way ahead of me then.
Yeah, very close.
Yeah.
But I wanted, as don't know anything about the quantum physics here.
Yeah, sure.
Can you explain a little bit more? What is destructive and why destructive is bad? You want to avoid it.
Yes. Good. So, destructiveness is bad because in a lot of situations in quantum computing and quantum information, I would like to make a lot of measurements on the same states, right? I have some states that I'm given, and it is very, very inconvenient for me that I measure once and then they're gone, right? There might be many different pieces of information that where I would like to learn all of them. And I would like to learn the earlier pieces of information in such a way that after I learn them, the states are still there for me to go and learn the later pieces of information.
When you say state, you mean you want to keep this whole matrix? Is it?
Yeah. I wanna keep my quantum state, which I'm now thinking of as just a physical state, like the state of some particles that I have been handed. And I want to measure them multiple times to learn multiple pieces of information from them.
When you say destructive, you mean the process made it deterministic, too precise.
Yeah, when I say destructive, I mean applying the measurement fundamentally changed the state, caused a large change to the state, where now I can no longer measure the state and learn the other pieces of information, or if I do, I'll just learn some garbage that is not informative about the original state that was there. Right? So I would like to learn many pieces of information about, my original state, without destroying it along the way. Okay, and in fact, later in this talk, I will give you an example of exactly that kind of task, something that I called shadow tomography a few years ago, and we will actually see how, the main results in this talk lead to a new protocol for doing the shadow tomography.
But that seems to me is very interesting. It's because the differential privacy is adding noise to mask the information, but here you are adding noise to keep the information. Am I right?
In some sense, I mean, in both cases, we are trying to prevent ourselves from learning too much. Okay. I mean, in differential privacy, we want to avoid learning too much because we want to, we don't want to leak users' data. In gentle measurement, we want to avoid learning too much because if we learn too much about which branch of the superposition we were in, then we collapse the superposition. Okay, so that is sort of, if you like, the fundamental similarity here. Okay, but I've gotten a bit ahead of myself. So let me switch gears from gentle measurement and talk about this completely unrelated topic of differential privacy. Okay, now differential privacy is a subfield of theoretical computer science that started around 2006. Actually, Cynthia Dwork, who is now here at Harvard, was one of the founders of it. And this is an attempt to apply theoretical computer science, to social problems about sort of protecting users' privacy. So you might say, about as far as you could possibly get from, applying CS theory to subatomic physics. Okay, the basic idea is that we have some database of, let's say, medical records. We want to learn something. We want to let researchers do statistics on it, or do statistics on Facebook data, for example. But we want to avoid them learning too much about any individual. Okay, actually, this is now these techniques are now actually used by Google. They're going to be used in the upcoming U.S. Census. Okay, so they're actually having some impact now. Okay, but it took people some years to figure out what was the right mathematical formalization of that concept of sort of preserving privacy, right? Because whenever you calculate statistics, well, you will learn something about individuals that you didn't know before. But can we formalize the notion that you will only learn a little bit? Okay, so sort of the right notion turned out to be the following. Given an algorithm A, which is querying a database, let's say a database with records about n different people, so x1 up to xn, we call that algorithm epsilon differentially private if it has the following property. For every pair of databases, x and x prime, that differ only in a single record, so they differ only by Alice having changed her data, or Alice having opted out of participating in this census. Okay, so for every two neighboring databases, and for every possible output y of the algorithm, the probability that the algorithm outputs y given input x is very close to the probability that the algorithm outputs y on database x prime. Okay, and the notion of closeness here is a multiplicative one. Okay, so we say that these should differ by a factor of at most e to the epsilon. So basically, if you like 1 plus epsilon, except e to the epsilon composes better. And so we are crucially thinking of A as now a probabilistic algorithm. That uses some randomness. Takes some random bits additional to x or x prime. And is using that randomness to achieve this guarantee. Okay, so let's again see an example. Okay, now we could, given a medical database, we could ask how many patients have prostate cancer, right? And that might seem like it's pretty, privacy protecting, but the trouble with that is, well, let's say that that Bob joins the database, and at the same time, this number goes up by 1. Well, okay, we've learned something about Bob. Okay, so a safer thing to do is to say, I will let the users of this database, calculate numbers, ask for numbers like total number of people with prostate cancer or more complicated things of that kind. But I will deliberately add some noise to the results before returning it. Okay, and a very convenient choice here turns out to be Laplace noise. Okay, so I could return, only the number plus some Laplace noise of average magnitude, let's say sigma. And then you can do a little calculation, and you can check for yourself that this algorithm will satisfy this definition with epsilon equal to 1 over sigma. Okay, so the larger is the noise, the larger is sigma, the more differentially private it is, right? The most private possible would be 0 dp. Okay, but 0 dp means that your distribution over outputs does not even depend on the database at all. So that's just vacuous. Okay, so you would like epsilon dp for epsilon that is as small as possible. Okay, okay. So now, given pretty much any notion in classical computer science, you can put like the word quantum in front of it and see what happens, right? That's been a reliable paper generating strategy for 25 years now. Okay, and so let's quantize the notion of differential privacy. Just in case we want to protect the privacy rights of electrons or something. Okay, and this is easy to do. We can simply say, given a POVM measurement M, which acts on n registers, so some quantum state of n registers, M is epsilon differentially private on a collection of states S, like for example the product states, across those n registers, if for every two states, rho and rho prime, on those n registers that are neighbors. Here, I have to say what I mean by neighbors. So let's say what I mean is that you can reach one state from the other by applying a quantum mechanical operation to only one of the n registers. Okay, that's what I'll mean by there being neighbors. Okay, so for any two neighboring states, rho and rho prime, and for any possible outcome y of this measurement, the probability that the measurement returns y on outcome rho is at most e to the epsilon times the probability that the measurement returns outcome y on the state rho prime. Okay, it's just the quantum version of what I showed before. Okay, what would be an example? Well, once again, given n unentangled qubits, if I want to measure the number of ones, let's say that will not be differentially private, but if I add a Laplace noise term, you can check that this will be differentially private even in this broader quantum sense. Okay, so you might say, so basically what happened was that I gave a talk a couple years ago at the Weitzman Institute that sort of was about, it involved gentle measurements of quantum states and mentioned this idea of achieving gentleness by deliberately adding noise to the outcome before returning it. Now, Guy Rothblum is one of the world experts on differential privacy. He was in the audience and he got all, excited, agitated. I think this is just like what I do. And I said, everyone goes to a talk and they think it's exactly like what they do, and it's probably very just completely spurious. But I said, let's meet for hummus and we'll talk about it. And to my great surprise, it turned out that he was absolutely right, and that we really were talking about almost the same thing in two completely different fields. So that's what this talk is about. Okay. So the main result that we were able to prove is that there is a two-way connection between a measurement being differentially private, at least on the set of product states, and that measurement being gentle on the set of private states. Okay, on the set of product states. Okay, this is not an exact equivalence. There are some caveats that we will have to walk through. There is some, loss of parameters in, a serious one in one of the directions. But, there is a two-way connection between these two concepts. And not only is there a connection, it is a useful connection. Okay, we can actually use it to port results from one area to the other in order to prove things that were not previously known. Okay, so the first direction of our theorem says that any measurement that is alpha gentle on all product states for sufficiently small alpha is also O of alpha differentially private on product states. Okay, that's a very simple statement. In fact, it doesn't even have much of anything to do with quantum mechanics. You could prove a classical analog of this. And in fact, if I crossed out the word product, then the statement would still be true. Okay. The second direction is kind of a trickier one. This says that there is a sense in which differential privacy implies gentleness. Okay, but the statement is this: if I take any measurement that is epsilon differentially private on product states, and if that measurement has a particular form, okay, so it consists of just a classical differentially private algorithm that is applied to the results of measurements that I could make separately on each of the n registers of my quantum state. Then that measurement is also O of epsilon times square root of n gentle on the product states. Yeah?
Is this square root of n partly coming from the fact that GP only cares about what happens to the neighboring?
Well, there is a sort of, that is part of what's going on. We can actually prove that square root of n factor is inherent, right? We can prove that it is unremovable. In fact, the Laplace noise measurement that I showed you in the previous slides can already be used to show sort of the optimality of this. Okay, so basically, if I add Laplace noise of order square root of n, right, then that is it gives me it gives me like order 1 over square root of n differential privacy, but it only gives me a constant amount of gentleness. Right, so that's so that example already shows it. Okay, so all right, so let me just make a few comments about this. Okay, so yeah, so the first comment, this is what I just said. Okay, that while there is this loss here, we can prove that it is unavoidable. The second thing is that this part 2 of our theorem really does depend on the states being product states. Okay, and this would actually be false if we try to prove it for arbitrary states across the n registers, or more precisely, what would happen is that I can prove an analog of this theorem for arbitrary states, but when I do, this square root of n becomes an n. Okay, so I get a multiplier of n here when it's arbitrary states, and you might say, what's the big deal? It's just a quantitative difference, square root of n versus n. Okay, well here's the problem. If I only have epsilon times n gentleness, right? Well, that is only interesting if epsilon is small compared to 1 over n, right? Because the least gentle that you can be is 1 gentle, right? So it's only interesting if epsilon is like 1 over n. Now the trouble is, if epsilon is less than 1 over n, well, the only measurements that are that differentially private are measurements that barely even depend on the input database at all. So like sort of nearly trivial measurements. Okay, we can prove that by just saying I could change every single database element one at a time, right? And even after changing all n of them, the probability of a particular outcome y would still have not changed by very much in such a case.
But I assume your product states are sort of sufficient, but not necessary, right?
Yeah.
It's sort of it's like an independence assumption.
Sure, absolutely.
The correlations to be okay.
Absolutely. There may well be a more general class of states to which this theorem holds. In fact, one of the, this has come up many times when I've given this talk, right? But one of the, a research direction that a lot of people would find interesting would be to generalize this to states that are only weakly entangled in some appropriate sense, or let's say where the entanglement would fall off rapidly with distance. Yeah, and I expect that could be done. Okay, now this restriction here on the form of the DP algorithm, this, for all we know, is only an artifact of our proof. Okay, so it's a nice open problem whether you can remove this. This looks like a severe restriction, but the good news is that basically all of the actual examples that we know of differentially private measurements actually are of this form. Except those that we specifically constructed to be not of this form, right? But everything that naturally arises that we could think of actually was of this form. So this is already enough to carry through the conclusions that we cared about, okay? But, nice question if we can remove it. The product states, actually to see that the product states part cannot be removed, it suffices to consider an example like the Schrodinger cat. An equal superposition of the all zeros string and the all ones string. That's the quantum computing Schrodinger cat, okay? And we could say, well, if I made a measurement of the Hamming weight plus a lot of Laplace noise, I told you that is very differentially private, but even with the Laplace noise, you'll still learn perfectly well whether you were in the all zero component or in the all one component, right? And because you learned that, we see that the measurement is not gentle. It collapses the cat. Okay. Now, when I've given this talk, to me it was like such a shock that these concepts were connected. And then I went and gave this talk, and people said, but aren't differential privacy and gentleness just obviously the same thing? Like, what is there even to prove? I should point out, first of all, that the notion of differential privacy makes no reference to what are the post-measurement states, right? It only talks about the probabilities of the different outcomes. Conversely, the notion of gentleness makes no reference to the concept of neighboring states, right? So clearly, there is work to do in relating these concepts. Okay. The work that is most closely related to what we do at a technical level was actually work that had nothing to do with quantum mechanics at all. Okay, but there was a beautiful sequence of papers initiated by Cynthia Dwork and her collaborators about 6 years ago that connected differential privacy to a problem called adaptive data analysis. Okay, an adaptive data analysis is basically where I would like to do many scientific studies on reusing the same data set over and over. But I would like to do it in a way that is safe from p-hacking, that will actually give me valid results, right? And the problem is, if I just do this naively, right, then each time I do a study on this data set, then the results of that study, if they affect what study I decide to do next, well then my statistical validity can go out the window for that reason, right? This is, I think people call it the Garden of Forking Paths problem or something, but, so this is a known problem in classical statistics. It has some connection maybe to the replication crisis in psychology. And so what Dwork et al. Showed was that amazingly, it actually is safe to keep reusing the same data set for study after study, as long as you are careful to only access the data set using differentially private algorithms. Okay? So, in effect, what they proved was that differential privacy implies a type of gentleness. But in their case, what they meant was classical Bayesian gentleness. Right? So if you take the distribution over possible data sets, conditional on the ground truth about the world, right? What they showed was that distribution, is only mildly altered by, applying a differentially private algorithm and then conditioning on its outcome, right? And therefore, we can keep applying such algorithms safely over and over again, many times. Okay? Now, this classical Bayesian gentleness is a little bit different from quantum mechanical gentleness. Okay, one difference is that, you could say damage to a probability distribution is something that occurs entirely in your own head, right? In the sense that you could always reverse the damage to a probability distribution by the simple expedient of forgetting whatever you just learned. Okay, right, this will sort of undo a Bayesian update. Okay, damage to a quantum state is much more objectively real in the sense that another person who measured the same state would be able to see that you had damaged it. Okay, but despite that, they are mathematically very closely related, and indeed we use some similar ideas in one direction of our proof.
Can I just add one point? I think
Sure.
that's a really great point. I did talk to Cynthia about.
Yeah.
There is a long literature in statistics is this kind of robustness methods. So what she was doing, what she discovered, was essentially you want the procedure, taking derivative with respect to data. You want the derivative to be small.
Yes.
Because you not sensitive to individual data points.
Yes.
The only way to do it is adding noise.
Yeah.
So that's
absolutely.
that's essentially is what this
Yeah.
is the thing.
Yeah,
doing.
like when applied to machine learning algorithms, like differential privacy can be thought of as a type of robustness property,
Exactly.
right? That is exactly what it is. Yeah. All right. Great. So all right. So I just had like 2 slides about the proofs. I mean, if you want to actually see the full proofs, you can, read our paper. But, I don't think that the proofs are the most interesting part of this work. But let me say a little bit about them. Okay. So the gentleness implies differential privacy is sort of the easier direction. It doesn't require the states to be product. It doesn't even sort of depend on quantum mechanics really. And the key to it is sort of the following lemma. Okay, so let me sort of define something that's sort of even more basic than differential privacy that I'll call, just triviality, right? I'll say that like a measurement is epsilon trivial if, for any 2 inputs, regardless of whether they're neighbors or not, the probability that I produce some output on the one input is at most e to the epsilon times the probability that I produce that outcome on the other input. Right. So in other words, just like differential privacy, but where I relax the neighbor restraint, the neighbor constraint. Okay, that is triviality. Okay, so like an epsilon trivial measurement for a small epsilon is one whose outcome barely even depends on input data at all. Okay, and now I claim that if a quantum measurement is alpha gentle on all states, then it is also this trivial. So, in particular, it is O of alpha trivial as long as alpha is small. Yes?
So if we're considering the gentle measurement in the example setting you described with the Hamming weight,
Yes.
like you would, if the set of all states is like the set of all the product states with different Hamming weights,
Mhm.
you would be able to tell the difference presumably between. Oh no, you wouldn't be able to tell the difference between the all zeros and all ones because it would collapse to them.
Well, let's see. So the Hamming weight plus Laplace noise, as long as the Laplace noise is small compared to n, that is not a gentle measurement, right? Because it's not gentle, it is consistent with this lemma. Okay? Yeah. Okay. And the way to prove this is basically just to consider the converse, right? So suppose that a measurement is far from trivial. Well, that would mean that, there are 2 states, rho and sigma, and one can actually argue that, like, without loss of generality, they're 2 perfectly distinguishable states. So, the ones that have a trace distance of 1. Okay, and suppose that the probability that M outputs Y is just very different on these 2. So they differ by a large multiplicative factor. Okay? And what you do then is you consider what does this measurement do when applied to an equal mixture of the 2 states. So rho plus sigma over 2. Okay? And well, what it does is, if I just apply to this and I use Bayes' rule, right? Because, we're just dealing with a classical mixture here, right? I use Bayes' rule. Clearly, when I condition on that measurement outcome y, I'm now going to get a weighted mixture of, the sort of post-rho state and the post-sigma state, that will be weighted much more toward the one, that had a higher probability of y. So I've sort of unbalanced this state. Because I've unbalanced it, I've produced a lot of damage. Because I produced a lot of damage, my measurement was not gentle. Okay? And that's sort of the contrapositive. Okay. And then to get this gentleness implies differential privacy for product states, what I do is I simply sort of apply this lemma separately to each register of the product state. So I say, if I took a product state and I fix the states in n-1 of the registers, and I only let the state in the remaining register vary, okay, well then, for a measurement to be trivial as I vary that one register, for any, but for, if it is trivial as I vary one register, for any value of that one register, then that is the same as being differentially private. That is what differential privacy means, right? And now, if I have gentleness on all product states, then I can use that to get triviality as sort of I vary any one of the registers, and that is the same as differential privacy. Okay, so now what about the other direction? That differential privacy implies gentleness in the special case of product states. Okay, so as I said, this direction is harder to prove. We know it only for measurements that act separately on each of the n registers. Okay, and basically, we use like a series of steps where we relate trace distance to the KL divergence, which is Kullback-Leibler, another measure of distance between probability distributions. Well, not a metric, but another way of measuring closeness of distributions. And then we in turn relate Kullback-Leibler divergence to yet another distance measure, the Hellinger distance. Okay, and so all of these sort of play a role. But what we do is we say let A be an epsilon differentially private classical algorithm. So we're just first going to take a classical warm-up to the quantum result that we want. We'll then lift it to the quantum case. Okay, and then this first step is basically like what Dwork et al. Did. Okay, so we say let A just be a classical algorithm that's differentially private, and then for any product distribution D on n registers, and for any possible output y of our algorithm, we can look at the KL divergence between D, the original distribution, and the sort of distribution D conditioned on I run A and then it outputs y, right? And the nice thing about KL divergence is that for product distributions, it just decomposes as a sum of all these individual, KL, rather expected KL divergences. For each I, the I is part of the distribution. I take the KL divergence between that and sort of the post-measurement, version of DI, right? Conditioned on both the measurement outcome Y and on all of the previous, samples, from 1 up to I minus 1. Okay, and then what you can do is you can say because of the differential privacy, these two distributions differ component-wise multiplicatively by at most factors of e to the epsilon, right? That's what differential privacy means. And because of that, it's just a calculus fact. One can then prove that the KL divergence here is at most epsilon squared. Okay, that's just a beautiful fact. It's very, very often used in differential privacy. And then I just sum up n of them, and I get epsilon squared times n for the total KL divergence. Okay, now what I do next is I sort of take this measurement A, and I lift it to act on a quantum superposition state, right? So I say, let's say I had this superposition psi, which is a product state for, the n registers. For simplicity, I'm assuming that it's a pure state. And then I also consider the state conditioned on the measurement outcome being y. And now I look at the trace distance between these two, right? And now just, it's a nice fact that I can do a calculation and I can upper bound the trace distance in terms of the square root of the KL divergence. If any of you have seen like Pinsker's inequality, this is related to that. Okay, and then this, I just plug this in, and I get epsilon times square root of n. So this is where that square root of n factor was coming from. Okay, and then finally, I just use some standard quantum information tricks to generalize this result to, not just like a standard basis measurement on pure states, but to POVMs acting on mixed states. Okay. All right, so now just in the last few minutes, I want to just tell you about the sort of flagship application that we were able to get for our connection theorem. Okay, and so like a few applications are almost immediate to see. Like one of them, I said before that Laplace noise measurement is a gentle measurement. I never proved that. Okay, now one can prove it by just a brute force calculation. But the nicest proof that I know is to say, well, clearly the measurement is differentially private, and so now, clearly it has this form, I separately, look at 0 or 1 on each register, I sum them up, so now I just appeal to our connection theorem, and I get that is a gentle measurement as well, okay? And, you can get other, conclusions about interesting measurements being gentle, that again, you might be able to prove barehanded, but, I think this is maybe, the nicest way to prove them. Okay. Now, now the one thing that we can do that we totally would not have known how to do otherwise is this improved procedure for a problem that I call shadow tomography. Okay. So what is shadow tomography? Well, so this is the follow. Okay. So first of all, ordinary quantum state tomography is the situation where I'm given a bunch of copies of a quantum state, say rho, say a d-dimensional quantum state, and my goal is by measuring all of these various copies, say some in one basis, some in another basis, I would like to learn rho, as a d by d matrix as well as I can. Okay, and this is one of the most studied problems in both theoretical and experimental quantum information science, right? It's known, it was actually only recently proven how many copies of rho you need for that d squared copies of rho are necessary and sufficient. That's sort of what you might have guessed, you're trying to learn a matrix with d squared entries, no duh, you should need d squared copies. That is surprisingly difficult to prove, okay? Only done a few years ago, okay? But using a lot of representation theory, actually, okay?
So the fact that you have a quantum state, with the constraints of being a positive matrix doesn't really help you reduce those parameters?
No, well, I mean, it's still order d squared, right? It's, d
Order,
squared.
yeah.
Yeah, it's still of order d squared, right?
Order,
The main issue is just that each measurement gives you this very limited information. How do I piece together the information from only d squared copies to actually learn the d squared entries of the matrix? Okay, but now the trouble is, for most interesting applications, d squared is just prohibitively large, okay? Think of if I have n qubits, then what is d? D is 2 to the n power, right? D squared is 4 to the n power, n is 1,000, that's already more than the number of subatomic particles in the observable universe, okay? So, Hilbert space is big, right? And so, so it's of great interest to know what can you do to learn quantum states even in the teeth of the exponentiality of Hilbert space. So a few years ago, motivated by applications involving quantum money and sort of quantum, uncopyable software and various problems like that, I defined a notion called shadow tomography. There's actually a physicist who named it. Steve Lemma, physicists are just better at naming things. So here is what shadow tomography means. I am given an unknown d-dimensional quantum state rho, and I also have a list of known measurements E1 up to EM. I'll for simplicity, I'll say these are 2 outcome measurements. So each EI accepts rho with probability trace of EI times rho, and it rejects it with probability 1 minus that. Say, okay, so it has those 2 outcomes. Now my goal is to estimate the probability that EI accepts rho for every I. Okay, so so I don't necessarily need to learn rho as a density matrix. Okay, but for each of the measurements in my list, I need to learn rho's behavior on that measurement. Okay, each one, let's say, up to some additive error of plus or minus epsilon. Okay, and now the question that I posed in 2016 was how many copies of rho do you need to do that? Let's say as a function both of d, the dimension of the Hilbert space, and also of m, the number of measurements. Okay, so just to get a handle on it, we can notice that d squared copies will clearly always suffice. So if I've got d squared copies of rho, I can just do ordinary tomography. And then I just learn rho, and then I know rho's behavior on any measurement. right? Now at a completely different extreme of parameters, order m copies of rho will also always suffice. Okay, why? Because if I have m copies of rho, I can just apply E1 to some of the copies, apply E2 to some separate copies, apply E3 to get more copies, and so on. You know, I don't care that I'm destroying them along the way, because, you know, I just do each measurement on separate copies. Okay, but now what if D and M are both enormous? Like in many applications, they would both be exponentially large. So the question that I asked was, could you do shadow tomography using a number of copies of rho that grows polynomially, only polynomially with log M and with log D? Okay, now, you know, that seemed like a tall order. My guess was that it was probably impossible, but, you know, I couldn't rule it out. I tried all the, you know, quantum information tricks. I couldn't rule it out. And eventually I figured out why I couldn't rule it out. And the reason is that it is possible. Okay? In the previous, you know, stock 2018, I had a paper where I gave a procedure for doing shadow tomography using this number of copies of rho. So it's like log of m to the 4th power times log of d divided by epsilon to the 4th power times some lower order terms. Okay, and you know, it was a fairly complicated procedure. It involved combining several, you know, previous quantum information protocols, you know, that had been known. Okay, but, you know, there were, you know, many things unsatisfying about it. One was this exponent of 4, you know, or this, you know, what's going on with that. You know, one was that this procedure, you know, required knowing all of the measurements E1 up to EM in advance. Right, and then, you know, just sort of processing them as a batch, right? You can't be handed them one at a time. And also, this procedure was not gentle. You know, it actually destroys the copies of rho. Okay, so now, in the paper with Guy Rothblum, we give a new, different way to do shadow tomography. Okay, the new way is actually online, meaning that the EIs, it can just, you know, you get E1, you estimate trace E1 rho. You get E2, you estimate trace E2 rho, and so on. You know, the EIs can even be given to you by an adversary who sees all your previous answers and who knows rho. You know, that's fine. Okay, so you get adaptivity, and it is also a gentle procedure, so you could do the whole thing, and then rho is still there to be used for something. Your copies of rho are still only slightly damaged and still available to be used for something else. And the number of copies of rho that you need, well, it's better in the dependence on log m. It's worse in the dependence on these other things. You know, I would love to, you know, strictly improve it. But basically, the way that it works is that we took a known procedure from differential privacy, which was called the private multiplicative weights procedure of Hart and Rothblum, which somehow my co-author, Guy Rothblum, knew about, you know, and understood well, okay? And, you know, it's a very clever procedure. It involves, you know, deciding whether to update your current hypothesis, you know, on each of the queries, EI, using a threshold measurement with Laplace noise added. We then defined a quantum analog of that procedure, creatively named QPMW. Okay, and then use, you know, each iteration of that is differentially private. Using that fact, using our connection between differential privacy and gentleness, you know, now that was not strong enough by itself to give us sort of, you know, the gentleness of the entire procedure, because we only get gentleness sort of round by round. But using this together with a lot more work, we were then able to show that you can safely apply all of the iterations of this quantum PMW procedure in sequence, each one damaging your copies of rho only slightly. So it's actually safe to do all of them, and you know, you get out all the information. Okay, so there's lots of exciting future directions here. You know, can you remove the restriction to product measurements? In our implication that differential privacy implies gentleness. I haven't said anything in this talk about computational efficiency. I've only been talking about like the number of copies of row, or it just purely information theoretic notions, right? But our implication from differential privacy implies gentleness could actually involve a transformation where you have to do something like you have to prepare a superposition over the outputs of the DP algorithm, which in principle that could always be done, but it might require an exponential blow up in running time in some cases. Okay, we don't know of a case where that happens, but we can't rule out that it does happen. So we would love to understand the computational complexity situation better. Then next, what is the true sample complexity of shadow tomography? So, in particular, we don't know that has to have any dependence on log D at all. Maybe you can do shadow tomography using only about log M copies of row, and that's it, right? That sounds too wildly good to be true, but I can't rule it out. And, shadow tomography itself seemed too good to be true, so who knows, right? If the shadow tomography also has to be gentle or also has to be online, then we can show that the log D factor is needed, again, by taking lower bounds that were known in classical differential privacy and porting them to this setting. What can we say about composition of multiple quantum DP algorithms? There's this is a major topic in classical differential privacy. There are new issues that arise in the quantum case that we don't fully understand how to deal with. And then finally, this was what Cynthia Dwork most wanted to know. Can we go the other direction? Instead of just stealing from differential privacy, can we give back to it? Can we use facts about gentle measurements in quantum mechanics to say something new about classical DP? So far, we haven't been able to do that, but I would love for any of you to. So, all right, thanks for listening. Question? Yeah.
Thanks for a fascinating talk.
Thank you.
The part you have not touched is you talk about this sample complexity, how many copies
Yes.
you need, but
Yes.
you haven't talked about how good are your estimator, like the errors.
Oh.
Do you pay a price for not
Yeah.
having?
Well, yeah, so I did include the dependence on epsilon here, right? So I said the task in shadow tomography is to approximate each expectation value, trace of EI times rho, to within plus or minus epsilon, right? And the sample, the number of copies of rho that you need to do that turns out to grow polynomially with 1 over epsilon. Okay, I don't know the optimal dependence. I suspect that it should be 1 over epsilon squared, actually. But this is what we're able to get using this quantum PMW procedure. Yeah.
What would be the classical scaling of K?
Oh yes, excellent question. In the classical case, it is very easy to get just K equals log M over epsilon squared. Okay, and why is that? That's basically just the Chernoff bound, right? It's basically just I have I have K samples from some distribution. Now I want to estimate, let's say, M different Boolean functions, of their average value on the samples. So I just go through, and for each one, I take the empirical mean, right? And by it, if I have log M over epsilon squared copies, well then, for each one, I'm going to be within epsilon of the right answer with probability at least 1 minus 1 over M. That's just by the Chernoff bound. And then by the union bound with high probability, I'll get it right for all of them. Okay? So, in that case, the fact that I used is that measurements of a classical string are not destructive. I could just keep, evaluating many different Boolean functions on the same string, and I clearly will not damage the string at all by doing that. Right? So in some sense, the open question that I am posing here is, even for quantum states where you can damage them by measuring them, can you get the same sample complexity? Can you get just log M over epsilon squared? Oh.
So in the online setting, are we imagining that you know how you know what n is, how many
Yep.
things you're going to end up having to measure? what if like you don't know how many measurements you're gonna
Oh,
have?
that's actually an excellent question. I should think. So what I have to think about is whether there is sort of anything in our procedure that requires you to sort of pick an a priori upper bound on M, on the total number that you're ever going to see. I should. I think that there is such a thing, but I can. If you want to just take 2 minutes after the talk, I can check that. Wait. When we set the parameters, is there I
Like,
don't
can you
remember
incorporate new copies of the?
Yeah, that's actually a great question. Right, like you could just pick an upper bound that is like so large that it's beyond what you. But the question is, do we in our parameter settings do we actually incorporate the future knowledge of what M is going to be? Give me 2 minutes after the talk and I'll answer that for you. That's an excellent question. Yeah.
So also for the online setting, so do you consider the case where each M is given adversarially depending on the previous?
Absolutely, we incorporate that case. Yeah, so
this
I
also-
mentioned that. Yeah. This can be the EIs are given to you by your worst enemy. Yeah, who knows everything you've done previously.
Sir, in the classical case, in the definition of DP, is there any notion of bit flips, like how different strings are related to each other?
Well, I mean, there is a notion of two strings being neighboring, right? And being neighboring means that they differ only in one database entry. If the database entries are bits, that would mean they differ only by one bit flip. Yeah, I mean, that is precisely how DP is defined.
And then you expect to get the tensor product structure for the gentle measurement because of this definition on bit flips that you have in DP.
I mean, you get the connection because of the theorem that we proved, right? I mean, it's I'm hesitant to sort of give a philosophical reason why it would have been completely obvious a priori, right? But I mean, yeah. Because also that same philosophical reason might lead you to state versions of the theorem that are not true, right? Yeah.
For example,
Yeah.
I just wanted to see if, for example, we know that the measurements are commuting or something like that.
Oh.
What's the corresponding thing?
Okay. Well, if the measurements are commuting, then like in something like when I talked about shadow tomography, you would not need the power of this theorem, right? You could just use the fact that the measurements commute. So of course you could apply many of them in sequence. So that would be an example where we would already know that you can do it with a much lower sample complexity than this.
If there are no more questions, let's thank Professor Aaronson again. And also, if you'd like to join for dinner with the speaker, we'll be meeting upstairs in 15 minutes or so.
Great. All right. Well, thanks. Hey. Oh, thank you so much. Hey. Oh, okay.